So let x and y be discrete random variables, and here observe that we're not assuming them to necessarily be independent. That independence assumption comes through in question B. So this is interesting. We're asked here to use LOTUS, 2D LOTUS, without assuming linearity, and to show that the expectation of x plus y equals expectation of x plus expectation of y, basically what linearity would give us. So we are in effect showing, giving a proof for linearity. Okay, so the expectation of x plus y, and these are discrete random variables. We will take the sum in that case over x, and the sum over whatever y is, and now x plus y over the joint distribution of f of x, f of y. Okay, so again, they are not independent, so we cannot just factor out the two densities and work out what the expectations are. So what we do then is that we just take the expectation of x, expectation of y, the two sums, just use the fact what summation gives us is that we can write them as two sums. This we can do because we have two sums and we are summing them up independently. Okay, now in this sum we are summing over the y's in the densities of y that we can do independently, and the same thing for each level of x, I should say. So for each level of x we sum over y, and this will give us a density over y equal, because it's a valid PDF, we can say that this whole thing will become over the y space equal to 1 when we sum over that. So what we're left with is the sum over x, f of x. The same argument holds for x in this instance. So what we are left with here is f of y, f of up, and the density of y, and these two are the expectation and the of x here, and that's the definition of y. And so we've shown that linearity works, and they basically came through by doing the summation in two steps. Now in the other question, we are now assume that x and y are independent. We're going to use LOTUS again. We're going to show that the expectation of x and y are can be factorized like so. Okay, x, y, and that is, we write it out as two sums again, and what we have is x and y and f of x, y. Now we were now allowed to use independence, so this factorizes like f of x, f of y, and we can rearrange this sum to be expectation over x and y. Whoops, ugly here. X, f of x, f of y, like so. Now first term here was just the expectation of x. And the other part here is the expectation of y. That ends our proof for the second part of this question.